For today's quiz, we're going to be talking about having either an engine or a motor. Normally, motors are electric, engines are maybe gas-powered or something like that. If you're an engineer, you might use these for a whole bunch of different applications, maybe a washing machine, a drill press, an automobile. Either way, you have that motor and it's always going to run at the same speed. But you need it to maybe change the speed or something like that. So our question today is, if we had a gear, should I put this gear onto a small gear, a medium gear, or even a larger gear if I wanted to get the maximum power? What do I mean by that? Imagine if you had an engine and maybe this over here is the engine and this is the output. Maybe I combine these with a belt or something like that, a chain, and I want to get the maximum amount of power out of it. Which configuration should I use? Should I hook the engine to a small, medium, or large, either pulley or gear? This is what your quiz looks like. As always, explain your answer the best you can and list your confidence. And remember, the engine's always going the same speed. Typical student responses include the following. A, it doesn't matter what gear you're using. The power's the power. It's never going to change anything. Some will say, but wait a second, I've ridden a bicycle and I notice if I change my gears, it's either harder or more difficult to either go up a hill or go faster. So some will say, no, I think you should have it in this configuration to go up a hill. Or maybe I need that configuration to go faster. And so they'll often end up using the word power for there. And others simply don't know. They still think that there's going to be something to do with power, but they don't know how to explain it. To help us explain this, let's draw a few things out. Why don't we separate these, and we can call them different gear sets. And that's really what they are, sets of gears. Kind of break them apart from one another. Let me just do it this way. Maybe on this side, let's give it some definitions and formulas. We asked for the power. So what is power? Let's go back to classic mechanics. We know power is just work divided by time. So I can say, well, power is equal to our work divided by our time. We probably should remind ourselves what work is. Linear work is putting a force on something parallel in the direction it's traveling. Even though we're going to be rotating, we should start here. So I could say, well, work is then going to be our force parallel to some distance. And because we're rotating, we should probably talk about what kind of work we're talking about. We're not doing linear work, we're talking about rotational work. So we have to start using our rotational analogs. So we should say that work is going to end up being a turning force. So maybe I can start with that. Work is going to end up being our turning force, which is going to end up being our torque. Maybe that's what we should do. Maybe we should start listing out our torque values. Why don't we start by saying, well, right here, we're going to end up eventually figuring out about our power, and we'll figure that out. Down here, we should probably maybe figure out what our work's going to be for each one of these. And then here, maybe we should start thinking about our torque. In order to do something with torque, I guess we should have a formula for that. And then we'll finish this formula up here. But we could say torque is equal to a force perpendicular to a distance. But if we're rotating, we can end up saying torque is going to be a force perpendicular to some radius. Maybe I need to put a line down here to separate what we're doing here. that. All right, let's start with our torque. Now remember, the engine's always going at the same speed. And by the way, we have an omega symbol for that. So maybe I'll draw that, and each one of these has the same omega. It's going the same exact amount. Omega, and that's how much it's rotating, its rotational rate. They're all the same. As is going to be the radius of our engine. So maybe I could say, well, this radius right here is R. This radius right here is also R. And this radius right here is R. And all we're doing is we're showing that our engine's doing the same thing every time. But what's not is the output shaft in this green color. So in that case, we know that torque is going to end up being some force. Now remember, the engine, there's a little E on each one of these. It's a little bit small, but the engine has the same amount of force, we'll say. So in each case, I can say, just for the green, well, this one's going to get the same amount of force. This one's going to get the same amount of force from the engine. And this one here is going to get the same amount of force from the engine. But what's going to be different, if we're talking about a force and a radius, the radius is different for each of these greens. Here I have a small r. Here I've got the same exact radius as I had on this other one. So I'll put that here as the same size, r. And this one is going to be way bigger. So I'll use a really big r on that one. Now what we can do is I'm drawing the size, because if I multiply the same size force by a really big r, and this one is multiplied by a medium r, and this one is multiplied by a small r, and we know that torque is going to be equal to our force perpendicular times our radius. Well, if I have a normal value multiplied by a small value, I end up with a small value, small amount of torque. This one would be our normal amount of torque. And over here, if I have a large value multiplied by a normal value, I'm going to end up with a very large torque. Now that I've got torque, and remember, I can end up saying that work is really torque times our theta. Instead of force, we use torque. Instead of distance, we use our angular distance, which is theta. Now, let's figure this out. If I have a certain amount of rotation, because another way that you can relate this is think about putting a piece of tape or something on this particular engine. If I ended up going from the 12 o'clock position over here, I've gone a certain theta that I've swept out from here to here. And I can do that. It's going to be the same on each one of these. I've got my theta from there to there. Theta is always going to be the same for that running engine. So I've got the same theta for each of these. Same theta. And on our blue, though, in order to get this same exact amount of arc that we've created going from here to here on our engine, on a smaller radius, it's going to end up going much further. It's going to end up starting here, and it might end up winding all the way down here. So you'll notice that our theta here is going to be huge. We're going to end up with a very large theta. On this one, it would be exactly the same theta as our engine. So this is going to end up sweeping out the same theta that we had over here. Maybe I should have drawn it a little bit bigger, but I think you get the idea. From there to there, it's going to be the same exact value as from here to here. If I, put a piece of string or something around that pulley. And over here, this distance here is not going to go quite as far in terms of our angle on a very large radius. So maybe it's going to start here, but if I only had that amount of rope, it's going to end up starting here, and it might end up only going over here somewhere. So I could end up saying that this is going to end up being a small theta. Now that I have those, I can end up figuring out my work, because my work, we can say, is equal to our torque times our theta. Well, we've already figured out our torques on each of these, so now I can go back to my green and work on those, and I can end up saying, well, this one I have, we said, is a small amount of torque. This is a medium amount of torque. And over here, I've got a very large amount of torque. But what did we say about theta? Theta was very big here. This would be a normal size theta here, exactly the same as the engine. So I could say, well, that's going to be our normal size theta, as compared to this one, which is going to be a very large theta. And over here, we're going to end up having a very small theta. So what do we get when we have a really small and a really big? The same thing if I have a really small and a really big. So in this case, it's going to be the same exact amount of work. And notice they're all the same work. But we didn't ask for work. We asked for power. So maybe we need to go back up to our power formula here. Another way to put this, now that we know that we can end up having work is equal to our torque times our theta. So I can do our torque times our theta all over our time, and then theta over t right here, my marker is running out. I can end up saying, well, that's going to end up being torque times omega. And that's what I can end up getting for power. And I already have my torque values once again. Now I can figure out theta. So again, I can end up finding power here. I've got my small amount of torque here, my medium amount of torque, and then my really large amount of torque. But what did we give up? Well, notice in the same amount of time, I've barely moved at all in our theta. So this thing is going to go slower. This is going to go a little bit more in terms of angle per time. And this one goes around much more. So here I'm going to end up having a large omega. So this one's going to end up going really fast. Where if I went to the other side here, well, this one is going to end up barely moving at all, and that's going to be a small omega. And this would end up having a normal size omega. So the work is going to be the same, and therefore we know that the power is going to be the same. So by changing our gear ratio, we don't change the power. What we do change is the torque, and that's interesting. And that's really your quiz for today. But I encourage you to stay, because I want to show you a real-world application of this. Because thinking about putting gears together is one thing, but how do you actually shift gears? That's what I want to show you. All right, this is something that is near and dear to my heart. I might be a little long-winded on this one, but this is something that I took apart when I was about 13 years old. Here's the manual for it. It's a transmission. And the very first time I saw something like this, I couldn't understand it. My father's an eccentric fellow, and as most kids were out playing, I came down in the morning and had a note on the kitchen table that said, take apart the transmission and fix it. And so I did. I put in the very similar vise here, and I remember pulling off the case right here, and I couldn't believe what I was seeing. And the very first thing that I saw amazed me. First of all, when I was holding the gears up, what you probably didn't realize is that they're curved, and they fit together beautifully. These are called helical gears. And so that right there was shocking to me. I thought all gears were straight cut. I later found out that helical gears are really quiet. Now this is a manual transmission, and I know that's kind of about as rare as a coelacanth these days. But, you know, back in the day, you had standard transmissions and you'd have to special order an automatic. And they were silent and they were wonderful, except for one gear, reverse. And reverse is still that same standard cut gear. It's not helical. And if you've ever been in a reverse manual shift car, you'll hear it grind, right? It really makes a lot of noise. But all the forward gears are quiet. And you can basically thank the helical cuts on these. Of course, they're going to be more expensive and so on. All right. But another thing that I wanted to show you right away is, and I might need to rotate this a little bit, is that, hopefully this is showing up on camera, all the gears are always touching. And this is what I couldn't figure out. How can that gear, that gear, that gear, and that gear all be touching at the same time? Couldn't figure this out. I had my father come home from work and explain to me what was going on with this transmission. But it's one of the great marvels of our time. And I have a few pieces here. First of all, I want to show you that one of the shafts, this right here, this shaft, and just to show you what I've done here, I have it connected to an electric motor. And this electric motor I have to a power supply, and I can then turn this on and get everything to move, as hopefully you can see there. I've done that by taking a little piece of hose here, really sturdy hose, and I have a gear-reduced motor that's going to end up simulating the engine or the output, however we want to do it. Regardless, this bottom shaft is a solid piece of steel. And you've got to think to yourself, how would you cut something like this with this precision? And this is out of a 1981. I remember the vehicle it came out of. So these cuts were made out of a solid piece of stock here. Now, I'll tell you how they did it. They softened the metal. They heated it up and let it cool very slowly. And you're going to end up changing the lattice structure. You can cut this, and then you're going to reharden it once it's done. So these gears are really hardened. And I don't know if it's picking it up on camera, but all of these gears have about 200,000 miles on them. And that's what's really fascinating, is that gears don't wear out for the most part, because it turns out you don't actually shift gears. Well, how can that be? Well, there's a marvelous structure on this next shaft that I want to show you. I don't know if you could see, but this gear is independent of this shaft right here. It is not connected onto there, neither is this gear. It's only when I take a collar here, and I take this collar and move it over. Now, the dog ears on this gear over here are connected through that collar. Now the shaft and this gear become one. That's what I'm shifting. I don't shift gears. I'm really shifting collars. Now I've taken and shifted over to this set of dog ears right here. So these are free floating, and all of this is going to be bathed in oil until you shift a collar. And that's what a stick shift does. It'll literally move those collars around. And I can show you those if I rotate this back around. This right here is my collar. There's another one down here. I'm hoping that this is showing up. But you'll see when I shift gears, I can pull the, I can go to first or second gear, and I'm just shifting my collar back and forth. Then I'm in neutral, and then I could shift from third and then fourth and so on. Let me see if I can get this moving so you can see the shift. Let me start this up. This is my output shaft right here. And you'll notice that I'm in neutral right now. Now, if I slide this collar forward, notice I'm in first gear. Now notice, I can't slow that down. Remember about having lots of torque? This is first gear. First gear has a huge amount of torque, but it's not going very fast. I'll shift it into second. You'll notice it's going faster, doesn't quite have as much torque. I can hear that I'm slowing down the motor that's driving this. I'll put it back in neutral. Now I'm going to put it in a third. You could see faster. And then fourth, really fast, but look, I can slow that motor down. And that's what a transmission does. it is simply going to allow us to change our speeds and our torques. And it's such a marvelous idea. Who would have ever thought of this? Well, it turns out that this wasn't thought of one person at one time. It's going to be thought of by so many iterations. We've talked about long-term projects in our podcast. This is probably version, 10,000. They keep making incremental changes and they make them better and better. I talked about that reverse gear, and reverse is right here. It also has other flat gears. Let's see if we can hear the noise. I got to make sure I do this right. Let me see if I can get this into reverse without jamming it. Oh, I jammed it. Hold on. Got to make sure I don't put it in two gears at one time. Let me slow this down a little bit. See if I can get this to go into reverse here. Oh, I'm in gear. There we go. And now I can... Oh. I don't have any safety locks on this. So, all right, let me see if I can... Got to hold this one in place and pull this one. Now, I've got it. I unfortunately just gave it a little bit of oil, and now it doesn't want to allow me to do what I want it to. I'll try this one more time. I'm in gear. That's my problem. Keep accidentally shifting it in there. So I'll throw this in here. There's my reverse. And so now I'm going backwards. And when you have this go faster and faster, you'll hear it clang. So now it's back in neutral. What a fantastic instrument that someone figured out. And remember, this is in neutral. So this going to your wheel right here, you could be coasting. The rest of the gears are, quote, engaged, but they're not. They're all touching, but none of them are being coupled through that coupler, which we call a collar. So we're really shifting collar. So you don't have to worry about breaking gears. You have to worry about breaking collars or those little dog legs on there. But I'm going to show you something else. Okay, I've talked about how marvelous this transmission is, but you notice that I can have my wheel spinning at any speed, and it can be independent of the rest of the transmission because I have a clutch, and we'll have to do a segment on that. But here's the problem. How do you shift gears when your wheel is going at a different speed than your engine? Before you had this next device that I'm going to show you, you would just grind them in. And if you ever watched really old movies, like The Three Stooges had a getaway car back in the 30s, and you would hear the car run, and then and you'd hear a grinding sound, because that's what they would do. They would just try their best to get the gear to match up with the speed of the wheel, and hopefully it would couple. And if not, you would hear this sound. It would be inside the transmission, but you would hear a grinding, because that collar is trying to get onto those dog legs. And if they're spinning at different speeds, they're going to grind away. Just so you know, that's what you're going to break off. You're probably not going to break the gears because they're already touching. It's this problem. And you used to have to be a fantastic driver to get these two to match. But then we came up with what was called a synchro mesh transmission. And this is going to end up being the key to making you shift in any gear at any time. It's called a synchronizer. And that synchronizer, if you look on the next to the dog legs, you'll see this smooth surface here, and it's got like a curve to it. And that curve exactly matches this piece of brass. And this brass has got little striations in it so you can hold oil. But it'll float on here when there's oil. Right now it's getting humid, and I've got a lot of moisture in the air. This is completely dry. There's no oil here, so there's some friction here. But even in oil, if I had this rotating on here, but if I put the slightest bit of pressure in this direction, that synchronizer becomes part of that gear. And if I don't put any pressure, they slide freely with oil. If I push in on it, they become one. And that is what this collar is going to do. Let me show you how difficult it is to get the collar on here when they're spinning. But when I have a synchronizer, watch what happens. As the collar starts coming on here, pushes on that synchronizer, and it's going to end up bringing it up to speed, and it just goes right on every time. So it's the synchronizer that really revolutionized everything. So while this seemed like an alien came down from another planet and just gave this to us, right? The person who figured out how to make a synchronizer to bring the gears up to speed, that is truly magnificent. And they're just such a wonderful invention. I want to say one last thing. If you like these ideas, especially about a synchronizer and these tolerances, and you've been thinking, gee, I wonder what I should be when I grow up, you should be a mechanical engineer. So let's wrap all this up and give you one last word. So what have we found? We found that your engine's always going to produce the same amount of power, or your motor is going to produce the same amount of power. What you do with these different configurations of pulleys or gears is you get to select how much torque do you want at the expense of how much speed. So this is going to end up having a large torque, but a really slow speed. So we could say this is going to be our first gear, and maybe this one would be second gear, and then we're going to end up having third gear. And you have more and more, but I think you get the idea. Third gear. Third gear is going to end up allowing you to go faster, but you don't have as much turning force, also known as torque. So the power is the same. You just select what you'd like to do with it. That's your quiz for today.